Jagdish sir, good morning sir. Am I audible sir?
Yeah, good morning, Krishna. And yeah, you are audible. Hope you are also.
Yes sir, you are also audible. Now we will start the session sir. A very good morning and a very happy new year to one and all. I am Mr. Ganesh, Assistant Professor, Department of Civil Engineering, JIT Institute of Technology. I heartily welcome all the participants and Dr. Jagadish Vengala sir for this 4th day's FDP of 1 week AICTE-ISTE sponsored refresher program. It's my immense pleasure to introduce the upcoming session delivered by Dr. Jagadish Vengala sir. Dr. Jagadish Vengala sir is currently working as an Associate Professor, Head EDC and Innovative Center in the Department of Civil Engineering, PVPSIT Institute of Technology, Kannur, Vijayawada. Dr. Jagadish Vengala sir obtained his doctoral degree on seismic response study of bamboo-based constructions from VTU Belgaum during 2015, for which he conferred with INAE Innovative PhD thesis by the Indian National Academy of Engineering INAE. He obtained his master's degree in construction technology from BMS College of Engineering, Bangalore in 2002 and bachelor's degree in civil engineering from Koneru Lakshmaya College of Engineering, Vijayawada in 1998. After 2 years, that is from 2002 to 2004, as a design engineer at Tar Steel Research Foundation, Bangalore, Sir joined IPIRTI under Ministry of Environment and Forests, Government of India as a scientist in August 2004 and worked for 11 years, that is from 2004 to 2015 for IPIRTI, Bangalore. With a passion in teaching, he left the government job and started formal teaching in 2015 at BMS Institute of Technology, Bangalore, and worked during August 2015 to May 2018. He worked as head of the department during 2016 to 2018. He has got more than 21 years of research, industry, and teaching experience. He was recipient of Outstanding Concrete Engineer, Andhra Pradesh for the year 2021 by ICI Vijayawada Center and Professor V. Ramakrishnan's Young Scientist Award for the year 2008 to 2009 by Indian Concrete Institute. He was recipient of 5th CIDC Vishwakarma Award under the category of Achievement Award for Scientist for the year 2013. He was recipient of Distinguished Professor Award by Amaravati Research Academy for the year 2020 and Outstanding Faculty Award for the year 2019 by Venus International Foundation, Chennai. In 2009, he attended as a member of the damage inspection team for the world's largest earthquake test on 7-storied wood building at Meikai City, Japan under National Science Foundation Project, USA. He was the recipient of a Biescast Fellowship in 2008 from Department of Science and Technology, under which he worked with Professor John Van D. Lindet, Department of Civil Engineering, Colorado State University, USA. He has delivered 190 invited and guest lectures at various national and international forums, chaired and co-chaired more than 25 sessions in international and national conferences. He organized more than 50 numbers of workshops, seminars, conferences, training programs. He has published about more than 50 research papers in various international and national journals and international conferences, out of which he received 5 Best Paper Awards. He has guided more than 30 MTech and BTech theses. He has got a patent on his credit. He was recently elected as National Governing Council member, Bamboo Society of India for 2021 to 2023. He served as Management Committee member for Indian Concrete Institute, Karnataka, Bangalore Center during 2007 to 11 and 2017 to 2019. He was the reviewer for the Journal of Structural Engineering, ASCE, the Indian Concrete Journal, International Journal of Earth Sciences and Engineering, Journal of Bamboo and Rattan, Journal of Cleaner Materials, and Engineering, E-Investigation and Materials Today Proceedings by Elsevier. He is the fellow of Institute of Engineers India, ACCA India, and life member of Indian Concrete Institute, Bamboo Society of India, IAWS, ISCA. His research interest includes sustainable building materials, self-compacting concrete, concrete technology, cementitious materials, earthquake engineering, bamboo-based and prefabricated housing. These are some of the extracts of his achievements taken from his profile. Dr. Jagadish Vengala sir, we are very much glad to have you in this occasion. Thank you very much for accepting our invitation to grace this occasion. Now I request Dr. Jagadish Vengala sir to continue this session. Thank you, sir.
Yeah, good morning, one and all. First of all, Happy New Year 2022. And I wish all the engineers, students, faculty, fraternity will get into newer developments, newer achievements for the benefit of the society. This is what everyone aim for, whatever work you do. Before starting my presentation, I would like to thank JIT Institute of Technology for giving me this opportunity to share my knowledge, whatever I have gained over a period of time with the participants. So let me share my presentation. Yeah, give me a second. Hope my presentation is visible. Can somebody?
Yes, sir, it is visible.
Okay. Yeah, I'm going to talk on sustainable concrete construction methods and practices. Basically, I'm talking about various concretes and what are the various methods to achieve and what are the various practices, and whatever I'm going to talk is based on my experiences with these concretes and some of the industry experiences wherein how the industry follows to achieve the sustainable concrete. Just to mention before the talk, once again, I am very thankful to JIT Institute of Technology and head of the department, principal and management, and also particularly Shrikesh, who is the coordinator for this program, for giving me this opportunity and sharing my knowledge with all of your audience, all the audience who are presenting for this particular lecture. So let me get into the technical talk. It is very important for all of us to understand this table in IS 456. Whenever you are designing concrete, whenever you are making concrete, particularly normal concrete, we are very much focused about this particular table. Largely the concrete, whatever we produce is reinforced cement concrete. So we generally design the concrete from minimum of M20 grade for reinforced cement concrete to different other grades. When we talk about reinforced cement concrete, we start with M20. So one very important thing all of you must know is when you design a concrete, we are designing the concrete for the exposure condition for which the concrete is going to remain there for the future. So when we are talking about the exposure condition of the structure wherein we are going to place our concrete, there are different exposure conditions IS mentions. It starts with mild and then moderate, severe, very severe, and then finally extreme conditions. So any concrete you design, whether it is M20 to M60 to M80, it is only based on the exposure condition we design the concrete. For a coastal regions, for example, if you take, we directly design the concrete depending upon the structure with severe condition. So that means when you are talking about severe condition, we choose the minimum grade of concrete as M30. And also we limit our water cement ratio to 0.45, which is there in the table. And we use the minimum cement content to 320 kg per cubic meter. What does that mean? All the concretes, whatever we design, are based on the exposure conditions only. You cannot randomly take M20 or M40 to design the concrete. And very important example I would like to mention over here is, for a normal weather, normal environment, you treat it as a mild exposure. For the same structure, the foundation which goes below the ground level, we treat the concrete below the ground level as a moderate exposure, because the concrete that is buried under the soil, which is under aggressive condition when compared to the normal weather exposure. So the foundation concrete, we treat it as a moderate. That is why the minimum grade of concrete, we go for M25, and the remaining structure, we go for M20. That is the same weather condition, but the foundation is below the ground, below the soil, and then the rest of the structure is above the soil. So even in the same structure, we have that kind of differences there. So that is why always the concrete exposure condition, based on that we design the concrete. Hope all of you understood by this time. And then we limit the maximum free water cement ratio to achieve the strength, because we lower the voids in the concrete, and we try to achieve the denser concrete, wherein to achieve the strength, to have the more bonding, more CSH gels, we also go for the minimum required cement content in the concrete. This is what the table meant for. I wanted to give you a kind of exposure on this table. So to sum up the table, the normal concrete, we generally go for minimum of 300 kg per cubic meter. And when you look into one of the clause of the IS 456, the total cement content we limit to 450 kg per cubic meter. That means the maximum cement content, not the cementitious content. And the water cement ratio, 0.5 grade of concrete, M20, to even now you can design the concretes more than M40. And IS permits the use of various mineral and chemical admixtures. We have a number of mineral admixtures like fly ash, silcophene, GGBS, ricers, metacovilin, and so on. So this is about the concrete. I'm just giving you in terms of how we design the concrete based on the exposure condition. And what are the ranges in normal concrete? The cement range is 300 to 450, and you start at the maximum of 0.5 for water cement ratio, and then different grades of concretes. And then why IS says mineral admixture, why you have to use. So I'll come into that. I'm talking about now the second part of my lecture, that is sustainable construction, sustainable concrete construction. Why one has to go for sustainable concrete construction? Very important. The construction industry, most of the construction towards concrete, because in our buildings or structures, we use the most material we use it in the construction is concrete. And energy we spend on this particular material is what we call embodied energy. So embodied energy is nothing but the energy we consume while extracting the raw materials. When you take the concrete, limestone extraction, to aggregate blasting, to various other materials, we use it in the concrete. And then producing materials, like producing cement, you go for 1600 degrees centigrade to, burn the materials, and then finally to get the clinkers. Once you make the clinkers, add other materials, gypsum and other cementitious materials, depending upon the type of cement, and then grind it So a lot of energy is consumed even in the grinding, and then finally you transport these materials to the work site. And also workforce is required to make the concrete and place the concrete. And you have to use a lot of equipment to make these. And while the structure is in use, you have to maintain these concrete structures. A lot of energy is consumed. And you have to finally demolish the structure when the life of this particular structure got over. So the entire energy you consume from the stage of extracting, demolishing the structure, this is called embodied energy. So think about the concrete structures. Most of the structures are concrete structures. So construction industry is consuming a lot of energy when we are talking about the most top 10 problems the world is facing. Energy is the first one to solve it. So wherein construction industry is the one of the industry wherein we consume a lot of energy. So when you look into the building life cycle analysis, as I mentioned, from raw materials to construction to transporting of these material, that means the concrete and then the operation of the building and then periodic maintenance and end of life disposal. So we are using a lot of energy and a lot of materials. Are we today throwing away the resources of tomorrow? Yes, certain extent. So our concrete construction, if it has to be sustainable, it should not be a linear economy, it should be a circular economy. That's what we are talking about, the recycled materials. So we are taking the material, we are making the buildings using it. We are disposing or demolishing the concrete waste. But it should be like you're making the materials, you're using it, and you have to recycle the concrete or reuse the materials. And it should be a like circular economy wherein we can save a lot of energy in the construction industry and we go towards the sustainable construction practices. So when you look into the last few decades, this shift is happening towards sustainable materials. When we start with cement, the most consuming material in the concrete, the shift is from ordinary Portland cement to now people are talking about blended cements, blending various other cementitious materials like fly ash, metacovalin, silica fume, GGBS, or such materials. Then the shift is from there to now people are talking about no cement. So without using cement, we are going for geopolymer concrete, wherein we are not using any cement, but we are using some of the chemicals to produce this, wherein the shift, that's what happening from ordinary Portland cements to then blended cements to now people are talking about no cement. When it comes to the concrete construction, so initially we are making a normal concrete. Now people are talking ready mixed concrete, wherein a lot of advantages are there, wherein you make this concrete somewhere away from the city or the workplace without pollution, without disturbing the surroundings, and then bringing the material to the site and placing it. From normal concrete to RMC to now people are talking about self-compacting concrete, wherein you need not vibrate the concrete, you need not use the workforce, and you get a better concrete, wherein which we are talking about this particular concrete in coming slides. And now people are talking about 3D printing concrete, a lot of advantage. You don't involve any kind of skilled workers, you can eliminate skilled workers, you just pour the concrete, it prints. And I teach and I did a lot of work in this particular 3D printing concrete, and even the Ministry of Housing and Urban Development and Poverty Alleviation and announced to go for 3D printed buildings in future in association with various research agencies and various academic institutions. And the shift is happening from natural river sand. When I came to Bangalore in 2000, the people are still using the river sand. When the restrictions imposed, so now nowhere in the site in Bangalore or some of the cities, you don't find any natural river sand. So you find alternative to sand, that is either crushed rock fines or robo sand or other alternatives to sand. And people are now talking about slag sand. And shift is happening from plasticizers to now you're having a super plasticizers and a new chemical admixtures, which will improve the properties of the concrete. And shift is happening from site mix mortar to people are now talking about ready mix mortar, wherein you mix two materials at the site itself and then, the ready mix mortar, you just have to add the water and then mix it and then use it for your purpose. As we are using a lot of energy to burn the bricks from clay bricks, wherein it consumes a lot of energy, from there to solid blocks to now people are talking AAC blocks, which they're having a lot of advantage when compared with both the clay and solid blocks. So we are shifting towards the normal materials which are energy consuming to sustainable materials which are less energy consuming. So the sustainability concept starts from the cement manufacturing. The article published by Chatham House, by Oliver et al., the analysis was done. Cement production and emissions, we look into it from 2010 to 15. So wherein the emissions are reducing. And it is taking a flat line from 10 to 15. What I'm talking about, it increased up to 14, and then there is a decline in the cement manufacturing. So this is because of various initiations in the cement manufacturing. So whatever emissions that are coming from the cement kilns, they're capturing and then they're storing it. So that is what we call it as a carbon capture and storage. And people are, it is in the research and demonstration stages, and people come up within no time. And people are talking about clinker-free cements, which will reduce a lot of emissions. And people claim that almost 90% emission reduction happened during these cements, during the production of these cements. We are already, substituting the clinker with either fly ash or slag. That's why we got the Portland Pozzolana cement. Pozzolana is the replacement of the cement with a fly ash. So the replacement can be up to 30%. That's what many of the cement industries are doing. When it comes to the slag, which is a byproduct from steel industry, we are replacing the cement clinker by almost 50 to 60%, depending upon the slag quality and depending upon the industry. They are producing Portland slag cement, that is PSC. So clinker substitution is also happening. And people are, as I mentioned, people are also talking about recycling or reusing of concrete, which needs less concrete, or designing the buildings using less concrete. So when we look into the various phases of the technologies that are developed, magnesium-based cement, so which is called NoSM. It is in research phase. Some of the Calaria cement based on carbonation of calcium silicates. It is in pilot stage. Some of the low carbonate clinkers, which are ethers, silicate, all these are in demonstration phase. And commercialized, what we talk about is high blending cements, geopolymers, or bellitic clinkers containing element, which are commercialized, which are sustainable in nature when compared with the ordinary Portland cement, which consumes more energy. So why I am giving all this is to the shift that is happening from the normal concrete construction, which is consuming a lot of energy, to sustainable concrete constructions, which needs less energy to produce these materials. As I mentioned, in IS 456 clause 5.2, we look into it. IS allows you to use supplementary cementitious materials. We have different materials like fly ash. You can see in the picture, microsilica, alcofines, GGBS, rice ash, metacavolin, so on. The most used materials are, as you know, fly ash and GGBS. And then with a 5 to 10%, we use alcofines, microsilica, and other metacavolin. Even rice ash also, we can go for 20 to 30% based on the studies, various studies. Why we have to use these supplementary cementitious materials? What the use and what is the significance, one should know. When we add water to the cement while making concrete, hydration process happens. Hydration, it occurs, as all of you know. It produces CSH gels. That is the final product, calcium silicate hydrate. Along with producing calcium silicate hydrates, some unhydrated material, that is calcium hydroxide or Portland JIT, is present in the concrete. When we add supplementary cementitious materials, either fly ash or GGBS, again, the unhydrated portion, that is calcium hydroxide lime or Portland JIT, that is present in the concrete, unreacted, again reacts with the silica in the either GGBS or fly ash and produces more calcium silicate hydrates. So in place of 100, you get 120 CSH gels, which will fill the remaining pores, and wherein the denseness increases and the concrete is more strong when you add the supplementary cementitious materials. When you look into the IS, you might get a doubt of how much it has to use these mineral admixtures. Is there any code? Yeah. If you look into the IS 10262, which we use it for concrete mix design, that is a new one, 2019. They have given the recommended doses of these mineral admixtures, even though for high strength mixes, whatever mix you prepare. So fly ash can be used between 15 to 30 replacement to cement. GGBS you can use up to 25 to 50. Metacavolin and silica fume, you can go for 5 to 15 and 5 to 10. So these are the recommended doses of mineral admixtures. If some client asks or someone asks, like, is there any proof that can I use? So you can tell that new IS 10262 gives you the recommended dosages. Otherwise, as long as your concrete is giving the required strength and durability properties, you can use any amount of these materials. So quickly, I would like to give you the example of how much the material, supplementary cementitious material used in Bangalore Metro Rail project phase 2. For piles and pier segments, the cementitious material used is almost 200 kg for M35 grade of concrete. Here they've used GGBS. And the pier end segments, M50 grade of concrete, they've used 400 cement and 100 GGBS. And they've achieved the required strength of 47 MPa in 28 days and 70 MPa in 28 days for both M35 and M50 grade of concrete. This is what I'm talking about, a major project which is used GGBS in a large quantities, that is 50%, and then the other 100 kgs out of 500 kgs. So these are the mixed trials they've done for the, see, these are my JSW friends wherein I was associated with one of the projects. So people are going towards sustainable construction methods, sustainable construction practices. Instead of using the energy consuming material, they are using the byproducts which are useful. So myself at JSW site at Thorangallu, Ballari, wherein we did small experiments on slag sand based materials. So even in the slag sand, now they are selling it, and then the slag aggregate, very interesting. When we are looking into the steel production, iron and steel, there are two kinds of slags you get produced. One is the steel slag, and the one is the iron slag. The slag which comes from steel production is heavy in nature, and the specific gravity is more than 3.5, wherein you cannot use it for the concrete construction, because if you make the concrete with the high density aggregates, your structure becomes heavy. So it can be used for the road construction. Very interesting when you look into the road construction that happened between Hospet and Ballari, National Highway 63. The Gaman utilized because it is near to the factory is near to Ballari. They've used the slag in various layers of the road construction. This is the first time in India entire road is made a complete slag-based road. This is National Highway 60. So coming to the that's what these are the uses of the cementitious materials. Why? What is the significance? Where and all it used? Now I'm talking about different types of concretes, wherein you need to use the more cementitious material, and also a lot of other advantages. I'm going to explain you. So now I'm going to explain you about the self-compacting concrete, which I have worked quickly. Maybe somebody remind me the time, because I keep on talking. Don't worry, once the time gets over, please remind me. So the flowable concrete, that means when you have to make self-compacting concrete, so it has to compact, it has to flow on its own weight and so on. So from normal concrete, suppose if you add the more water, can it be the self-compacting or self-flowing concrete? No, because when you add simply adding the water, the cohesiveness may not prevail in the concrete. That leads to either segregation and bleeding. So once it becomes hardened, all these pores that created in the concrete, that means the water gets away and then it leaves the pores. So when the load got applied, okay, and then in the hardened state, a lot of other durability problems that will occur to the concrete. So how do you make the concrete? You have to, use, to make the concrete, you have to use the chemical admixtures. So chemical admixtures, I have not explained. I'm just giving you the chemical admixtures is a broader term. Only super plasticizer or plasticizer cannot be a chemical admixture. There are a number of chemical admixtures. which are used in the concrete, starting from plasticizer to super plasticizers, which are water reducing admixtures or high range water reducers. If you wanted to delay the hardening process, we use the retarders. If you want to accelerate the hardening process, we use the accelerators. If you wanted to induce the air inside the concrete, we use the air entraining agents. And there are a lot of other chemical admixtures which are used for different special applications depending upon the type of concrete. So you need to know what exactly, if you don't add the admixture, how the hydration reaction it happens. When you add water to the cement, it flocculates. What is this flocculation? Because some 20 to 30 particles stick together with a 2 to 3 water droplets. So wherein the water gets trapped between these flocks. So mixed water gets trapped within these flocks. So this trapped water may not be available for giving the required workability in the concrete. So we are achieving the work, we would like to achieve the workability with the given water content. But water got trapped between the flocks. So this is what the chemical admixture, whatever we are using it as a plasticizer, it plasticizes. What does that mean? When you add this chemical to the concrete, it will not allow the cement particles to get flocculated. So it deflocculates the cement. So that entrapped water, whatever that is there between these flocks, gets released and cement particles moves freely so that you have the enough workability when compared with the previous. So workability increases with the same water cement ratio. Your workability increases, more water is present to get hydrated. So your cement hydration property also gets improved. The reaction that happens inside, why it gets deflocculate, because of the interparticle repulsion. Different charges will occur between the cement particles and chemical admixtures and water, and it gets away from each one, and then interparticle repulsion will happen, water gets released. This is the basic reaction when you add the plasticizer or super plasticizer. Depending upon the type of plasticizer, depending upon the type of super plasticizer, the reaction or action will be more, sometimes less, depending upon the concentration also. This is a microscopic view of the with and without super plasticizers. You can see the flocks, you can see the deflocculated cement particles. So what we are achieving by adding super plasticizer here, when you take a normal concrete, in the first case, it is a 0.55 is the water cement ratio, slump to be achieved 75 mm, and your strength is 51 MPa, you have to achieve the 28. By adding plasticizer, in the first case, you are increasing the slump. That means you are not changing any water cement ratio, but you are achieving the same strength. So in the first case, you can increase the workability without altering the strength. Point number one. In the second case, you are reducing the water cement ratio, but maintaining the same slump, but you are increasing the strength. So point number two is, without altering the slump, you are achieving the more strength, that is 63 MPa. So here, the role of plasticizer or super plasticizer, two things it can do. By maintaining the same water cement ratio, by achieving the same strength, it can increase the workability. Point number 2, by maintaining the same slump, by reducing water cement ratio, it will increase the 28 days compressive strength. So 2 things it can do. Please follow it, whatever I'm saying. Here, very interesting thing one must know. People bring the concrete and then throw it on the reinforcement. That's what the workers do. Do you know what is the free fall height of the concrete? That means from which place, from the what height you can throw it onto the concrete elements. That means the reinforcement. So it should not be beyond 1.5 meters, please remember. So when you throw it or when you place it from a certain height, the concrete go and hits the reinforcement. If it is a congested, the mortar portion sticks to the reinforcement and the aggregates will separate it. So if your mix is not good and if your free fall height is more, this is what it happens. So how do you achieve a cohesive concrete wherein it goes and falls without any segregation or bleeding? So you have to increase the cementitious materials, or you have to incorporate more fines. That means you have to impart the cohesion in the mix. Or you have to enhance the flow. So you have to use these cementitious materials in a right quantity. Otherwise, more cohesion also leads to reduction in flow. So you have to be very careful in utilizing these cementitious materials. As we have seen, let's say why the self-compacting concrete has come into picture. Because of the poor compaction that is happening in many of the structures. And also a lot of large and complex structures are coming up, and all these structures are having congested structural reinforcement. Can you assure the proper vibration that is happening in these congested structural reinforcement? It is impossible. So these are the kind of structural reinforcement you can see, congested one, in many of the complex structures. Complexity is becoming more because of the high rise, because of the various industrial structures. There is a metro congestion in reinforcement. So the solution is self-compacting concrete, wherein it is highly flowable. While flowing, it is still stable, and it can go and fill nooks and corners of the formwork without, you don't require to do any consolidation, and it will not get separate out. This is self-compacting concrete. In late 80s, that means 96, 98, so on, it is introduced into this Japanese construction industry. The motivation behind the origin is there is a reduction in skilled workers in Japanese construction industry, which led to reduction in the quality of construction work. So that is the reason, because the quality is reducing, or because of the skill is you don't get a required skill to place the concrete. That is the reason they've started the self-compacting concrete. What are the various other advantages? It eliminates the compaction, we know, and it will shorten the concreting period, and there is no noise that occurs. You just have to pour it, and you need not vibrate it, and compaction is assured. These are all the advantages. But how different is concrete from the normal concrete? One has to go for a high powder content between 450 to 600 kg per cubic meter. So normal concrete we allow up to 450 only. And then here, either the coarser and fine aggregate ratio is equal, or sometimes coarse aggregate is lesser when compared with the fine aggregate. And you have to use admixtures, both mineral and chemical. As I mentioned, the powders are essential in self-compacting concrete to make the coarse aggregate in a suspension mode without separating it out. And this coarseness, we get it from the large powder content that we are going to incorporate between 450 to 600 kg per cubic meter. But when we have to go only with the cement, it is it is not possible, because 450 kg is the limit. Beyond that, it leads to heat of hydration, drying shrinkage, creep, all these things will increase. What are the various other materials I've already spoke about? That those are mineral admixture. Out of these, as India's energy consumption mostly depends on the thermal energy. Thermal power stations, based on thermal power stations. So we have a lot of thermal power stations which generates the power. So the byproduct which generates from these thermal power stations is fly ash. Because we get a coal, we burn the coal, the byproduct is fly ash. So annually more than 100 million tons of fly ash is being generated. When compared with the other supplementary cementitious material, this is most abundant. And particles diameter is between 1 nanometer to 150 nanomicron. And from what we collect the fly ash from ESPs, electrostatic precipitators. So there is increased availability in all of the India. When it comes to Andhra, we have like VTPL, Vijayawada thermal power stations, and Telangana, Ramagundam thermal power stations. In Karnataka, we have very Raichur thermal power stations, and there's a Meturu thermal power stations. There are different thermal power stations which are there across the India. When you look into the morphology of the fly ash, it is smooth in nature, glassy surface. This is a SEM photograph, so which gives the ball bearing effect to the concrete. I've already mentioned, when you add the water to the cement, CSA gel it forms, and unhydrated cement. When you add more pozzolana, or the fly ash in this case, so it produces more CSA gels, which imparts the strength. Low cost when compared with the other supplementary cementitious materials. You can use large amounts like 150 to 350 kg per cubic meters when compared with the other cementitious materials. As I mentioned, the silica fume and other materials, you can go for only 5 to 10%. So that is why SCC, when you're producing, fly ash is an ideal powder in self-compacting concrete. So what are the things required to achieve the self-compacting concrete, which is beneficial, which is sustainable, what I'm talking about, because you're incorporating the more cementitious materials, which are the byproducts from different industries. Requirements are filling ability, stability, and passing ability. Filling ability is it has to flow and fill all the spaces within the formwork without any external help. That means under its own weight. Passing, it has to pass through the tight openings of the reinforcement between the steel reinforcing bars. So while passing, it should not get segregated, or the coarse aggregate should not get blocked on its way. It has to remain homogeneous in composition during transportation and placement. This is segregation resistance. Test methods, we use slump flow, that is a normal Abrams cone, J-ring, V-funnel, L-box, U-box, fill box, and ornamentals. And we're just quickly going through it. There is a normal Abrams cone, very famous, 300 height to 200 top and bottom dia. We do normal concrete slump, that is a vertical slump. Here we measure the horizontal slump. The slump range should be between 600 to 800 mm, depending upon the application. You place the concrete, you lift the cone, it spreads horizontally. You take the average of 2 dias orthogonally. You can also measure the time required to flow. This is a secondary measurement, time required to flow to the diameter of 500 mm. This should be between 2 to 5 seconds. This is a small video. I'll just Due to the time limitation, I'll skip it because you know that the pictures, through pictures you can see, right? Yeah. Second is a V funnel, wherein you measure the viscosity of the concrete. So here, any fluid or liquid, we measure the viscosity. There is a time required to flow through the narrow end. We measure here. So this is a typical V funnel. You can see wherein we pour the concrete into the V funnel, and then we measure the time required to flow through this V funnel. So here, actually, the value of the V funnel flow. So you make the concrete, immediately you pour the concrete, and you remove the bottom door and measure the time. There is one more measurement. What does that mean? You place the concrete into the V funnel. You have to wait for 5 minutes. You take the 5 minutes gap, and then you open the bottom gate door. So what will happen in these 5 minutes time, if the concrete is not good, all the aggregate gets settled at the bottom. It blocks the flow. So it increases the flow time, okay, required to flow through this, the bottom, portion. So it should be less than plus 3 seconds. Suppose normal V funnel time is like 8 seconds. This should be 11 seconds, less than 11. It should be between 8 to 11 seconds. If it comes at 15 seconds, that means there is a lot of blockage. The concrete is not. Anyway, I'm skipping the video due to the time limitation. Next is L-box test, wherein here you measure the passability of concrete, wherein you measure even the time required to reach the 200 mm and 400 mm in the horizontal box. And also we measure the height difference between the vertical end and then the horizontal end. That we call it as a blocking ratio. You can see the both ends, you measure the height difference. And then the H2 by H1, it gives the blocking ratio. This should be more than or equal to 0.8. So this is how you measure the blocking ratio of the concrete. Next is U-box. You have two limbs of U-box, wherein one limb you pour the concrete, lift the gate, and it has to flow through the other limb, through the reinforcement that is there, that gate that is there between, which separates both the limbs. So the difference in the height of the limbs should be less than 30 mm. So when you lift the gate, the concrete has to flow through the gate, and then it. So next is J-ring test, wherein you just give me 1 minute. This is J-ring test, wherein you place the slump cone inside the J-ring, pour the concrete in the slump cone, lift the cone. It has to pass through the J-ring. So you measure the height difference between inside the ring and outside the ring. So it should be less than 10 mm. You measure, because once you lift, the concrete flows through the J-ring that contains the reinforcement. And the height difference inside and outside will give you the value that is like less than 10 mm. There's a fill box test, wherein it contains obstacles in the box, and then you pour the concrete and it has to fill even though the reinforcement is congested. So next is screen stability test, wherein the 10 liters of concrete is taken in a bucket, wait for 15 minutes. As I mentioned, when you wait for it, if there is a problem, the coarse aggregate particles get settled down onto the bucket, below the bucket. And then the top half portion, you sieve it through 4.75 MC. If you only get the mortar, then it is a problem because all the particles get settled down. So your concrete is not good. So the percentage you calculate between the sieved and then total. So it should be between 5 to 15%. So these are various ranges, typical ranges for various tests. That is slump flow, T50, J-ring, V-funnel, L-box, U-box, and fill box. I think Sanjay Varma, do you have any question? Maybe I'll answer at the end if you don't mind. Yeah. So the acceptance of these tests can be a combination of, any of 2 or 3. In Japan, they use the slump flow, V-funnel, and U-box. Sweden, they go for slump flow and L-box. Some European countries, they go for J-ring and U-box. We recommended slump flow. Either U-box or L-box, you can do it. And then V-funnel 5 minutes is one of the good tests wherein one can go for SCC to accept. Applications are plain till now. This is the Osaka gas station in Japan. I happen to visit this place. This is the first application of SCC. This is in 98. So we started the SCC work in 2000 in BMS College of Engineering. The first congested reinforcement, what you have seen, this is the finished one. This is another one, Akashi Kaiko Strait Bridge. This is the pier they've used in 98. So it connects 2 islands. I happen to visit this place also. It's the longest suspension bridge with a length of 3.9 kilometers with a 1.9 span. 240,000 cubic meter of SCC used. I'm talking about 1998. This is a DMRC, Delhi Metro Railway application. The inside tunnel lining in Delhi Metro. This is tunnel lining in Sweden. So the precast elements that are casted in Sweden. These are the precast elements, poured concrete, lifted after the. This is one of the commercial complex in Italy, wherein the work completed within no time by November. The work, it started in Jan and it finished in October. So within no time, because the pouring is very fast. These are the prefabricated benches. This work is done at University of Catalina, Spain. Now the professor is in IIT Chennai, Professor Ravindra Gettu. He did this work during that time. So these are the precast prefab benches using self-compacting concrete. So we did the self-compacting concrete in 2000. Wherein we come out with a kind of a method of mixed design. Wherein from normal concrete, the workability we have set to 75 to 100 mm slump. We've used the marsh cone test to get the required superplasticizer dosage. And then we achieved 160 to 180 mm with the superplasticizer dosage. Then coarse aggregate is replaced with various part replacements with fly ash. And then we check the properties of SCC in each stage by replacing coarse aggregate with 5, 10, 15 to 25. So we have got the desired self-compacting concrete. As we know, any mix we design based on IS ways here. The coarse aggregate content is more. Here in here in the self-compacting concrete, either the coarse aggregate is same with the fine aggregate or sometimes it should be lower. So that is the concept. We replace the coarse aggregate with fly ash. So we did all the trials we conducted all the tests for each trial. So we have used a Raichur Thermal Power Station fly ash, OPC 53, and that time, as I mentioned, this was done in 2000. So we've used the natural eversand. That is that time in Bangalore, it is available. So these are the mixes you can see: 430 cement and 160 fly ash, fine aggregate, and then the coarse aggregate. So coarse aggregate is much lower than the fine aggregate. These are the slump values, L box, V funnel, and GTM values. Very interesting thing, that is the long-term strength of the self-compacting concrete. In one of the mix, you can see mix number 6, 55 is our 28 days strength, 270 days it is 90 MPa. We just pour the concrete. So this is the advantage of fly ash when people are going for a long-term strength. So we've almost replaced the fly ash with 46%. 46% of fly ash is being replaced. 90 MPa. I'm talking about 2000. So when we talk about the hardened properties of the SCC, it behaves compared with the normal concrete, and almost all the the properties are more or less same. That is why the SCC has become the choice for complex structures, wherein it produces high performance and durable. So we are talking about the sustainable way of producing the concrete, wherein we are incorporating more mineral admixtures, which are byproducts from various industries. And the paste is more, 38 to 45%. Normal concrete, if you take, it is only 27 to 29%. You can calculate the paste content. Paste is nothing but cement plus water. So in this case, cement plus water plus mineral admixture. So fibers is one of the very good use in concrete nowadays, whether it can be a natural fibers or the artificial fibers that are coming up in the market. Because you're improving some of the properties of the concrete structures. You're making the structure, increasing the longevity, increasing the durability by incorporating these fibers. So you're improving the post-cracking behavior. You're reducing the permeability of concrete and increasing the durability or the longevity of the concrete by incorporating fibers. When you look into the stress strain curve, so there won't be any sudden failure. It gives enough warnings, enough indications. Number of fibers are there: steel, glass, carbon, cellulose, polypropylene, nylon. These are synthetic. Now people are talking about coir. We did one work, hay fibers, and people are using human hair in the concrete. I'll give you one example wherein we test. So these are the different fiber types, from steel, glass, asbestos to acrylic. Each of it having a merits and demerits on its own way. Some fibers having more ultimate elongation, some having more tensile strength, some having specific gravity more. When you look into these fibers itself, glass fibers having more tensile strength, and steel is having more Young's modulus, and acrylic is having more ultimate elongation. So which application you are looking at is very important. What are the factors of the properties? How much you added, how much volume, what is the aspect ratio, how the fibers are oriented in the mix. These are all important. So we use only less than 1% in case of the slab applications. That means the horizontal applications. We use 1 to 2%, that is moderate volume we talk about. We use it for shotcrete applications. Suppose if you wanted to shotcrete some of the tunnel lining applications, wherein it has to go the concrete and hit the surface and it has to get stick. Okay, so in such cases, we use 1 to 2% of the fiber volume. More than 2%, high performance fiber reinforced composites, if you wanted to make, we go for more than 2% of volumes. When it comes to the aspect ratio, the optimum aspect ratio is 75. That is length to diameter ratio. Beyond 75, it will decrease. The relative strength or relative stiffness. You can see that. Orientation also, it matters. That means it depends on, is it direction of the load or the perpendicular to the load, or is it randomly distributed? So parallel to applied load, it offers more tensile strength and stiffness when compared with the randomly oriented. And again, are you using a low module fibers or high module fibers? There are different applications for these fiber reinforced concrete applications, both in India and abroad. So some of the Madura project road construction they've used. See, by utilizing a small amount, you are increasing the durability of the structure. So you are, actually increasing the longevity which is required. So you can see some of these fibers applications. But this is what I'm talking about. The method I mentioned in the title. What kind of method you have to follow when you're using the fibers? Here, the mixing sequence is very, very important while making any kind of fiber reinforced concrete. In a mixer, you have to first place 50% of aggregates and then 20% of fibers, then mix it. Again, remaining 50%. Again, remaining 20% fibers. Mix it. That means rotate the drum. Again, 50% sand. Again, 20% fibers. Again, rotate the drum. Again, 50% sand, and then 20% of fibers. Again, rotate the drum. This is how it distributes homogeneously within the mix. So then last cement, remaining 20%, again rotate. So your dry mix is completed, all the fibers distributed properly, and then add the water and then make the concrete and place. Very important. Many people, they dump everything into the mixer and then they make the concrete, and these fibers locate somewhere, this, that, very bad. So this is one of the methods when you have to follow when you're going for fiber reinforced concrete. You can see the pictures will speak, with and without fibers. Sudden failure, you can see the after compression test with fibers. Tensile strength also, you can see the crack behavior with and without. Impact got failed, you can see, how with and without fibers. Shear strength failed completely, shear test. So this is how it remains. Cost and steel fiber reinforced concrete is used in Tehri Dam or Uttarakhand. So next is ultra high performance concrete for special applications. They talk about reactive powder concrete with the different combinations. So wherein they use, this is a high rich mix. These are the different types of concretes: high performance concrete, self compacting, ultra high performance, reactive powder concrete. Different, here you can see reactive powder concrete. Coarse aggregate is not there. So you have more of powder and then sand, and then water and then superplast. So different applications, different the concretes, and the volume fraction is, you can see the volume fraction. For thin applications, thin elements, as I mentioned, aggregate is eliminated. This is ultra high performance concrete for architectural or structural applications. Pervious concrete has become one of the need of the hour nowadays. So to make the pervious concrete, one has to design, or we talk about water drainage rate. So this is used for some of the very important applications like driveways and other applications. Density should be less, 1,600 to 2,000. and it has to allow the water 320 to 120 liters per meter square of area per minute. Porosity also between 25 to 15%. You are incorporating porosity. Different applications: sea walls, bridge and embankments, swimming pool decks, residential roads. It will drain away the water. You can see that. And the colored concrete, lot of applications. You add the pigment, which gives the required color. It's an integral pigmented concrete. We also call it as a decorative concrete. So you get a nice finish. Next is polished concrete. So why I am saying all these concretes, instead of using one more material and then do it, grind it, one shot you can finish. If you want to, depending upon the applications, you straight away go to the concrete and then finish it. This is a polished concrete, a very nice polish. This I have taken it from our Ultratech friends. You can see. Stained concrete, you can do the etching by incorporating a particular acid into it. You can see the required staining you can get in the concrete. Sinks, vessels can be made using the concrete. This is a stamped concrete before just setting time starts. That means the final setting time. So they place this mold or whatever shape is required. They'll stamp it on that, the fresh concrete, and then they get the required shape. This is the translucent concrete, wherein using glass fibers, acrylic rods, and optical fibers. Very interesting, application, that is a fiber reinforced bendable concrete, wherein the concrete can bend. That means many people are working wherein replacing the steel. Very interesting, thought, wherein you have to completely replace and then make the fiber reinforced concrete without any steel reinforcement. This is 40% lighter and 500 times more resistance to concrete. By adding polymer microfibers, you can make the bendable concrete. Yeah, 3D printing concrete, as I mentioned, out of different concretes, wherein now it is becoming reality. So many places they have done the work. Loughborough University, wherein 3D printer will build the physical objects directly from computer generated instructions. So this is a part of additive manufacturing, wherein a special type of concrete. That means once it comes out of the nozzle, it has to set. It deposits, it gets deposited, and it has to immediately get set. Very interesting application. Sorry, the videos. I'm skipping. So now coming to some of the practices and some of the work one has to do in the future. What are the areas? Many people they design the mixes, and this is a very, very important application. People forget, because when somebody asks you to do the mix design, accelerated curing test is very important for all of you to follow it, because you cannot wait for 28 days. Okay, so one has to know about accelerated curing test to reduce the time of knowing the strength, and also to give the future result, because this is an established method. So you need not wait for the 28 days. Anyway, you can wait. You can compare it over a period of time. So here, what we do, we cast the cubes, and then the bottom base plate of this concrete mold removed and placed in boiling water in 100 degrees centigrade in a 3.5 hours. Then you remove the molds, cool it in 27 plus or minus normal water for a period of 1 hour, then take out, then air dry for half an hour, then compression test is carried out. So based on the formula, R28 is equal to 8.09 plus 1.64 times accelerated curing strength. So you can see average R28 value 38.6, but actually it is 43. So what I'm saying, you can project the 28 day strength much before, so that you can make number of mixes to avoid the the time delay. One can follow the accelerated curing test. So now I'm talking about some of the work, some of the 1 or 2 case studies what I've worked on. Very important, very interesting combinations we worked on. This is a precast bamboo reinforced furniture elements we made, wherein reinforcement is the bamboo strips. And then we poured the self-compacting concrete and we designed the precast benches. This is one of the work we carried out. So bamboo strips we've taken as a reinforcement. We made the reinforcement case. We put it in the mold. And we poured the self-compacting concrete with the method I have explained you in the previous slides. And we did the curing using the membrane curing for a period of 7 days. So we made the grooves initially itself, and then we've assembled these precast elements. This precast bench dimensions also we arrived based on the ergonomic considerations by taking the femur length and knee length of the various people. Those are coming for the park, for a particular park. So this is called ergonomic design we did. So we arrived at the bench dimensions and we poured the concrete SCC using bamboo as a reinforcement. Then we did the load test. 400 kgs up to 720 kgs we've loaded, and then we placed the dial gauges and then measured the deflection, very minimal. And then we removed also. So this is one of the application. Okay, various small applications. If alternative reinforcement material is available, using mineral admixtures in the concrete and in a larger way, and pour it, no need to vibrate. So very interesting application we did. One has to think about such applications. This is also very interesting work, that is use of GGBS in manufacture of solid concrete blocks. Don't think when we are talking about the construction, so concrete blocks also falls under the sustainable concrete practices, because huge quantities we are using it in the construction. So wherein here we've visited different number of sites to understand the solid blocks, how the behavior and other things. And then we understood, we have come out with a kind of the problems from the various block manufacturing units. And there is no particular mix design for these blocks in various sites. So we came to know people are using 100 kg per cubic meter to 200 kg per cubic meter of cement in a per cubic meter of mix, which you make solid concrete blocks. Then we started varying different cement contents from 100, 150 to 200. And then we prepared the cubes initially to get the optimum mix. So for that, we have simulated the field conditions into laboratory, and then we did not vibrate it because you are going to press the block at the site. We just vibrated 3 to 4 seconds similarly. Then we completed laboratory trials, and with the optimum mixes, we have gone for full-scale trials at site. These are the mixes wherein we have got 13, 33, 50, 57, and 73% replacements of cement with the GGBS in the solid concrete block. Then we went with the optimum mixes to site. So 2 of our students, we've deputed there, and then they did a lot of trials in making the blocks. You can see here. So these blocks were brought back into the laboratory and then tested. Very interesting, not 3 cubes, not 3 blocks average. When you're talking about solid concrete block testing, you have to test 8 blocks. The average of 8 blocks will give you the average compressive strength of the block. Please remember, it is not like average of 3 cubes. That is for concrete cubes, but for blocks, you have to take average of 8 blocks. So the various strengths we got. 14 MPa, you can, and very interesting, work which is benefited to the society is we have replaced up to 50% of cement with GGBS per block. We got profit between 2 to 5 rupees, and per month, almost 33 lakhs per year. So the kind of savings, why? Because the cement cost is 300 plus 350, 340. Half the cost is your GGBS. When you reduce the percentage, like half cement and half GGBS, you are mixing in solid concrete block. So then some of the sites we've implemented with the help of JSW. So whatever you are doing, it has to see light into the society, whatever small research. This is one of the research work we did. These are like durability studies. And manufactured sand we used and mineral admixtures in a ready mix concrete. We have visited 2 to 3 ready mix concrete plants. We collected the samples. We understood the durability behavior of these mixes with mineral admixtures and manufactured sand, and given right suggestions to these manufacturing ready mix plants, saying that this is the percentage of M sand you are using, these are the percentage of mineral admixtures you are using, these are the results of RT-PCR acid test, so that you increase this, you decrease this, you do that, you do this. These are the suggestions we gave. This is one of the paper we published recently in Journal of Engineering. Yeah, this I wanted to, yeah.
Sorry for the interruption, sir. Sir, we have left with another 5 minutes. We have still have a discussion session, sir.
Okay, I'm closing it in 2 minutes.
Okay, sir. Thank you, sir.
So this is the almost last slide. Thank you for reminding me. So here, increase the thermal, so to know the thermal comfort behavior of the buildings, we've used solid concrete blocks, AAC blocks, clay bricks, and using a different insulation material, different coatings in the buildings to reduce the cooling load inside the building. So we did a lot of studies. This is one of the area wherein people can work to know the behavior of the sustainable practices, sustainable concretes, or sustainable building materials. Using use of nanomaterials in the concrete with the fibers gives a very good results, and which will improve the properties of the concrete. And utilization of bagasse ash, that means the natural fibers in bricks, concrete. This is also one of the very good work one can. So with that, some of the references. Thank you. I hope I have not bored you, but hope the learnings must, give some kind of thought process in each one of you, and you should do some kind of work which should finally lead or finally benefit to the construction industry in particular, and benefit the society in large. The floor is open for questions. Yeah, thank you.
Thank you very much, sir. Really, it was a very informative session. We have received few questions from the participants, sir. We will take one by one.
Can I read and can I answer? No
Sir,
problem.
I will read, sir. Sir, the first question is, sir, can you explain little about grading of different kinds of fine and coarse aggregates for replacing both fine aggregate and coarse aggregate at a time?
Yeah, grading is a very good, very important parameter in the concrete. You see, when you're talking about the grading, there is a very interesting test one can do. Taking the one of the container which we use to find the uh, density of the coarse aggregate. So Contrao and other people have done a lot of work on this, wherein you start adding, the percentage of coarse and fine aggregates like 60-40, 60 to 40, 38. So with the different proportions, and start measuring the weights, start measuring the densities. So wherein you place it and then find the best combination which gives the more density. So more density, less voids, the combination, the test will give you the better grading. So that is about the combination of fine aggregate and coarse aggregate test. But when we are talking about the individual gradings, like fine aggregate. So fine aggregate, we have a zone 1 to zone 4, all of you know, and you have to do the sieve analysis and you have to understand about the fine aggregate, sieve size and grain analysis. And when it comes to the coarse aggregate, always you have to go for the graded aggregates. Whatever we collect from the market is a single sized aggregates. That means the same size throughout the aggregates. But you should have the combination of different size fractions in the coarse aggregate. That is why when you talk about the 20 coarse aggregates, usually single sized aggregates, you mix the 50% of 20 down to 12 to get the graded aggregate, different size fractions, leads to less voids, and then you place you combine the fine aggregate and finally get the dense concrete. This is the general application. Yeah, hope it answered the question.
Thank you, sir. Next question is, sir, pore structure of the aggregates play an important role in strength contribution in concrete. Sir, in SCC, if we want to incorporate construction and demolition waste, do you suggest repetitive recycling of aggregates for performance enhancement? How can we optimize the recycling of aggregates?
Yeah, any recycle aggregate contains more or less, because we cannot wash it. You just crush it, and the same you're going to use it. When you wanted to wash it and when you have to make it more proper, you have to use a lot of energy, which is not required. So when you're using any construction and demolition waste, you have to understand that the aggregate already is stuck with a mortar all around the aggregate. And it is very important to measure the average moisture content or average water absorption. So once you find the water absorption of these aggregates, definitely you can control or hold about the water cement ratio, and the required flow you can get it. But sometimes the viscosity modifying admixture plays very important role, wherein any change in the moisture, what we call moisture change, it will take care of. This is viscosity modifying admixture. And also repetitive recycling of aggregates, it can be used, but at the same time, as I mentioned, you have to find out the water absorption of these aggregates. And because it is a water sensitive, right? So average water absorption, you have to, because when you take the bunch of aggregates, you have to find out and then understand the water absorption and then add the required water. And to small changes, you can, by adding the viscosity modifying admixtures, you can control the flow properties and other properties. You can optimize in that way.
Thank you, sir. Next question is, sir, can you give a brief overview on how to do the cost analysis and life cycle assessment of a newly developed sustainable material? Is there any IS code regarding the same?
So any new material that gets developed or any sustainable materials, people are working a lot, on the one. See, life cycle assessment is one way, and then cost analysis is another. So whenever you are talking about cost analysis, one has to keep it in mind. That is, one is the production cost. So people stop there. That means once they calculate the production cost, oh, this is high in cost. No. So you have to find out what is the payback period of this particular method or this particular material. What does that mean? So once you make a different type of concrete and make it into use, so because of the advantage of such material, otherwise you don't use the new material. So what is the advantage? How much it advantage is in terms of cost? Okay, so for 1 year after its use, okay, these are the benefits you got in terms of cost. After 2 years, how much? After 3 years, how much? So by paying more water, by paying more amount, okay, initially, you are somebody is disturbing. Okay, by paying more amount initially, by make that into use, you are actually getting back the money within 2 or 3 years. So what I'm suggesting is you have to calculate what is the payback period of such concrete or such material, newer material. And in terms of life cycle assessment, you also have to calculate the embodied energy of all these materials. If it is a new material, you have to calculate once, and then operational energy. That means once you put into use, so at the end of the life cycle, till then, how much it gets benefited in terms of cost, in terms of energy, and so on. So IS code, no, but ISO standards are there. One can follow it, and a lot of LCA methods and LCA softwares are available, like SimaPro and other softwares, wherein it can simulate the new materials behavior. Yeah.
Thank you, sir. Next question is there any estimate on carbon footprint reduction due to use of sustainable concrete for different construction activities? Any case study?
Yeah, as I mentioned, like, when you're using a SimaPro or such similar materials, you can also get how much carbon footprint value you got it by using such materials. So a lot of literature is available, and also if you use it in some project, I can, if you can get into the BIM-based projects. So all these people are now using BIM, building information modeling, BIM softwares, and they are finally talking in terms of they're asking about how much carbon footprint reduction you got it. So a lot of case studies are there. It is available in the net. Yes, I can provide you the information.
Thank you, sir. Next question is, sir, as per IS 815, it is mentioned that we have to test a minimum of 8 specimens for concrete blocks. What is the logic behind selecting average of 8 number of concrete blocks instead of 3 number of specimens for measuring the compressive strength?
Yeah, because the solid concrete blocks, when you're making, it is not as quality conscious as when we are making the concrete. What I'm talking about is, so in the manufacturing unit, the edges will go off, and because by merely selecting 3 blocks and testing it, you may not get the correct value. And also the block making machines. So when we visited a number of small block manufacturing units, so we understood that there is a lot of the the variations within the manufacturing unit itself and within the different manufacturing. By looking at all these, the quality consciousness to know the quality in a better way. So they have taken 8 specimens instead of 3 specimens because the quality matters, right? So that is why. And also the cost also, it may not be more because each block, it comes around 30-35 rupees, and you have to test 8 blocks because you are supplying. So these many blocks, like 2000 blocks are for a project, you have to test only 8 blocks, something like that. So you have to randomly pick and do it. That is why they because of the quality, and also the edges may sometimes they are having a problem and so on. Yeah.
Thank you, sir. One more question is, I observed that the low calcium fly ash is more reactive than high calcium fly ash. Is there any relation between C bar S ratio to the reactivity and strength of concrete?
Yeah, a lot of literature is available because fly ash is being utilized for a long time. In many of the projects, it's very proven, and yeah, there is a relation. People have done it. Again, it is also depends on what is the reactive silica content that is present in the fly ash, and again the low calcium is having the more silica in it when compared with the high calcium fly ash. And also it depends on the, how much is the reactive silica and how much is that also matters. And also it depends on what quality of, I discussed the same thing with one of the researcher in JSW. He mentions like the coal what they import from Australia has got more reactive and what we call a more calorific value, and then the more reactivity and so on. So it depends on the source of coal and then the burning and then the reactiveness of it. So a lot of literature is, see, Government of India having a division called TIFAC. Okay, so in TIFAC, they've sponsored initially a lot of money to do research in various research organizations like DST based and a lot of engineering colleges. And a lot of literature is being published in this TIFAC. You can go to TIFAC website and you get a lot of information. Yeah, thank you.
Thank you very much for answering all our queries, sir. Being civil engineers, we all know how important it is to produce a sustainable concrete by using less energy consuming materials to reduce carbon footprints. Hope all our participants got benefited from your thoughts about usage of sustainable construction materials and practices, sir. Sir, once again, on behalf of AICTE, ISTE and Department of Civil Engineering, Jyoti Institute of Technology, we are very much thankful to you, sir, for accepting our invitation. We expect same kind of support and association with our institute for conducting more and more programs in the future also, sir. Thank you very much, sir.
Thank you once again. Thank you for the management of Jyoti Institute of Technology principal and then head of the department, and particularly Sri Keshava for inviting me to this AICT program, and hope the participants got benefited. And in future also, they can mail me or message me anytime. See, end of the day, we are all doing for the benefit of the society. Thank you so much, and namaste.
Thank you, sir. There is an announcement for all the participants. Attendance and feedback link is shared in Zoom Meet chat box. The next session will start exactly at 11:30.